Let's get started with new lecture material. New lecture material, we're continuing with probabilities. Now, what did we talk about last time?
Sample space.
Sample space. We talked about sample space. What's the definition of a sample space? What is a sample space?
Set compared to probabilities.
It's an ordered pair S and P where what?
S is the set. That's what you're
S
using.
is a non-empty set and P is a function of. NP is S is.
Keep going. P is a function where what?
P is a function where such that P of S is greater or equal to 0.
Ah. Say it in words. So P is a function like this. So you notice that P goes from S to R. What does that mean, first of all?
S. Real numbers.
Yeah. It takes everything in S and pairs it with a real number, which we call its probability. So P is a probability function. So S is our set of possible outcomes. That's how we think about it. It's a set of all possible outcomes. P is our probability function. It assigns to everything in S some real number, which we call its probability.
Okay.
And its probability has to follow two rules. Rule number one, there's no such thing as a probability less than 0. There can't be less than 0% chance of some outcome occurring.
Yeah.
Number two, the sum of all the probabilities has to be 1. If there's only 2 possible outcomes for flipping a coin, heads or tails, then the odds of it coming up heads or tails has to be. If I flip a coin, what's the odds that it comes up heads or tails?
Oh.
What's the odds I get one of those two things?
50 chance. 100%.
Oh.
100% chance. If it comes up heads or tails, I win. If it comes up something else, you win. Let's flip the coin. How often do I win?
100%.
100% of the time. So the probabilities have to add up to 100%. So that's a probability function. So you have your probability function, your set of possible outcomes, together as an ordered pair. We call that a sample space. Now today we're going to talk about an event. Once again, an event, very simple definition. Let SP be a sample space, then A as a subset of S is called an event. An event is just a subset of your outcomes. Very simple definition. We'll see an example where this is useful. So you might remember last time when we were talking about creating a sample space for rolling 2 die, and I said, what should S be? Then some of you said, if you're rolling 2 die, the possible outcomes are 2, 3, 4, ... 12, right? And I tried to point out to you, yeah, you could do that, but it's better to just do S is equal to the set 1, 2, 3, 4, 5, 6, crossed with 1, 2, 3, 4, 5, 6. So it's the set of all possible ordered pairs you can make with the numbers 1 through 6. So something like 2, 7 would be something in S. So S would, not 2, 7, 2, 6. So S would have 2, 6 in there. It'd have 1, 1. It'd have all possible 36 rolls you could have. You remember that conversation?
Yeah.
But you notice that there was still something useful about thinking about it this way. You still care about the event that someone rolled something like a 5. Right?
Mm-hmm.
When you're playing the game or whatever. So that's what we can use now an event for. So now if the event A is rolling a 5, if this is S, S is all the possible ordered pairs of 1 through 6. It's all the ways that the dice can come up. The dice can come up 2, 6 or 1, 1 or etc. Then we can make A the event rolling a 5. What would that be? That would be, you can get a 5 by rolling 4, 1, 3, 2, 2, 3, and 1, 4. These are all the possible ways that you can roll a 5 with 2 die, right?
Yeah.
So here's one possible event, rolling a 5. We can also have the event rolling a 12. Rolling a 12 would just look like this. So now we can use the notion of an event to capture rolling a particular value, and then our set of possible outcomes can still be all the possible die rolls. Does that make sense? That's an example of using events. So let's follow through with the example we had here. So rolling a 7 with 2 dice. 2 die. So let's imagine that our sample space is this. S is equal to 1, 2, 3, 4, 5, 6, crossed with 1, 2, 3, 4, 5, 6. Fortunately, that's not plugged in. We just open the blinds there, let some light in.
It's not.
That doesn't roll.
Yeah.
You want to prop that door open as well?
We only have so much heating.
Well, better that you can learn than you stay warm, right? That seems to do more. Will you look on that camera? I don't know.
There's
Can you-
almost there.
Ah, it's enough. You can see. Alright. So we have the set 1, 2, 3, 4, 5, 6 crossed with 1, 2, 3, 4, 5, 6. Our probability function, probably should have said that, P of little s is just going to equal, what's the probability of a particular roll?
1 out of 36.
136, right? What's the probability that you roll 1, 4? 1 in 36. What's the probability that you roll 3, 3? 1 in 36. So the probability of a particular outcome is 1 over 36, comma, for all little s in big S. Right? Here's our sample space. Now let's talk about the event. We'll call it A. What is the event rolling a 7? Tell me what to write. Now I want to talk about the event rolled a 7.
You want to get all of them?
Yeah.
1, 6.
1, 6.
6, 1.
Let's,
6, 1, 3, 4.
you guys want to do it again?
2, 5.
6, 1. 2, 5.
5, 2.
5, 2.
4, 3.
4, 3.
3, 4.
3, 4.
4, 2.
Okay.
4, 2.
So there we have the event rolled a 7, right?
Yep.
Now, question, what's the probability that probability of big A? What's the probability that we rolled a 7?
6 over 36, so 1, 6.
1, 6.
Right, each of these has a probability of 1 over 36.
Alright.
So the probability of event A is,
1, 6.
it's 1, 6, but I
6.
want to show you the notation for it. I know that you can
Oh, right.
add that up. I just want to show you the notation so that you understand when you see it later. It's the sum for every little a in big A. For every little a in big A, it's the sum of the probability of little a. So it's the sum of the probability of that, plus that, plus that, plus that, plus that, plus that. In this case, that's equal to,
1, 6.
well, let's write it first as 6 over 36, just to make sure it's very clear. 6 over 36. We had 1, 2, 3, 4, 5, 6 of these. Each of those had a 1/36 chance. So when we add all those up, we get 6 over 36, which is 1/6. So you roll 2 die, there's a 1/6 chance you're going to roll a 7.
Okay.
Make sense?
Yeah.
Yep.
Good. All right, let's try another one. Tossing a coin 5 times. So what do? We toss a coin 5 times. So what is S going to look like for us?
What if heads and tails?
S is going to look like, yeah, you could have gotten heads, 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 heads. You could have gotten heads, 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 tails, dot, 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 all the way down to tails, 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 right? Now question, what's the size of S? How many elements are in S?
25?
Yeah.
25.
Oh no.
2, 2,
2 to the 5.
2 to 5, 2 to 5.
2 to the 5. 2 to the 5, which is equal to,
4,
164?
no,
248?
64.
no,
512?
2 to
5,
2,
6,
4, 8, 16.
64.
I'm not done. 16, 32, 64.
That's what I said.
It's not 64.
2 times 2 is 4.
2 and 2 is 4.
That's
2 and
square.
2 is 4, so
8.
36.
8 and 2 is 16.
16, 4.
16 and 8
32,
and 2
yeah.
is
Okay,
32.
32! Wow!
Guys, you made
You guys were all over the place.
Sorry.
I like that. Finally, we got someone thinking. Yeah, stop sitting back and letting these guys do all the thinking. All right, 32. If we were to write all these out, there would be 32 possible outcomes. Right?
Okay.
Yeah.
Okay, so now let's look at the event They flipped exactly 1 heads. A is they flipped exactly 1 heads.
Okay.
What does A look like?
2,
Heads,
4.
tails, 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 heads.
Heads, tails, 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 tails. Perfect. Tails, heads, tails, tails, tails. And we can continue on all the way down. If we just shift the heads each time, our last one's going to be tails, 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 heads. More importantly is what's the size of A?
5. Oh, 5 over 32.
The size of A, not the probability, just the size.
It is 5.
5, yes. So now notice that what's the probability of A?
5 over 32.
When all the events in S are equally likely, we should have set the probability function first. So the probability of little s is equal to what? What's the probability of one particular little s in here?
1 over 32.
1 over 32. And that's true for all s in big S, right?
Yeah.
When your probability function is even like this, then the probability of an event A is always just equal to the size of A over the size of S.
So yeah, I got 32.
Which in this case is the size of A was 5, and the size of S was
32.
32. So there's a 5 in 32 chance that if you flip the coin 5 times, you'll end up with exactly 1 heads. Make sense? All right, let's try another one. Let's say that B is the event we flipped exactly 2 heads. So one example of something in here is going to be heads, heads, tails, 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 and then we keep writing all the way until we get tails, 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 heads, heads. Okay, so B is the event we flipped 2 heads. What's the size of B?
4.
No, it's going to be a
Yeah. Goes.
Oh, God, I didn't think about that.
Yeah, what's another way that we can think about this? Think about this as a counting problem. I have 5 positions I have to fill for each of my 5 coin tosses.
Okay.
2 of them need to be H's. And then the rest are tails. How many ways can I choose 2 of these to be H's?
5.
8.
5, choose 2.
5 choose 2.
Right.
Perfect. So the size of B is 5 choose 2, which is equal to,
I don't remember the formula.
you don't remember the formula? So when you have
5 factorial.
n choose k, it's equal to n factorial over n minus k factorial times k factorial. There's the formula.
Oh, well.
Okay.
So 5 factorial.
So you have 5 factorial over 3 factorial times 2 factorial. Right?
There's
You missing
facts.
anybody?
Nope.
Missing the power.
That's
Yeah.
You guys are 10.
Hole in here.
And so the answer is,
Obviously 10.
up here, 3 factorial is going to cancel out with 5 factorial, leaving 5 times 4. That cancels out the 3 factorial. And then 2 factorial is equal to
2.
2.
2. So 20 over 2 is equal to
10.
10.
Whoa.
There's only 10 options.
There's only 10 ways
I
that you
was
can do
gonna
that.
say 10, but then I was like, there's no way, because that's just multiplying 5 times 2. That's not how I do it.
Yeah, sometimes you can have bad intuition that leads to the right answer, but... Anyways, so that's how many ways we can get 2 of them to be heads. So now what is the probability that 2 of them are heads?
10 over
10
32.
over 32.
10 over
5
32.
over 16.
Or 5 over 16.
Or.
Or,
There's no or.
That's the best way you're going to represent it. We don't want it as a decimal.
or 1 over 3.36666 repeated.
True. He has a
That
point.
one's fun.
That's fun.
You say true, but
It's all fun when you understand what you're doing. Stop, think for a minute, and then it gets fun. Because you understand it. And you'll just think to yourself over and over again, oh, that's cool.
It's cold.
Toughen up. Do I need to get my little toddler to come tell you that?
Would not
Yes, please, that would be so cute.
That's just what I needed this morning.
A 3-year-old to come in here and say, toughen up. All right. Next, let's see. our next sample space is going to be for rolling 10 dice now.
Oh wow,
Alright, you got 10 dice that you roll all in one go.
that's a lot of numbers.
Oh, jeez.
So S is going to be equal to
4.
1 through 6 cross 1 through 6 cross 1 through 6 10 times.
Yeah.
So it's going to be all the 10 tuples, the list of 10 elements we can create with the numbers 1 through 6.
Can you
So
go
6
1 through 6
to the power
and
of 10.
square it?
So it's going to be
10.
1, 1, 1, 2. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That will be our first one. Comma, and we'll keep going until we get to
Oh, until you get to
1,
12.
2, 3,
Oh,
4, 5, 6, 7, 8, 9, 10, 10. Okay. And we want to calculate the probability of you rolling a 57.
Okay.
No, not really.
Okay.
We won't make you count all the ways you can roll 57 with 10 dice.
So sad.
But how big is a set S?
6
What's
to
the
the
size of this?
Lots.
Lots not a size.
6 to the 10.
6 to the 10?
Or 6 times to 10.
6 times 10. There's
Oh,
only
yeah, there's
60
60.
things in there.
Yeah.
No, there's a lot more than 60 ways you can roll 10 dice.
6
Bad
to 10.
intuition, throw that out.
There's 6
It's 6 to the 10. Don't give up so easily. 6 to the 10.
Chandler said something to herself.
Oh, you didn't?
Yeah.
I thought you did.
Chandler.
Oh, okay. Anyways,
You went
6 to 10. Make sure this makes perfect sense.
Moment.
You have 10 rolls. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many ways can you roll this die? 6. And for each of those 6 outcomes, how many ways can this dice come up?
7.
6.
And for each of those 36 outcomes, how many ways can this one come up?
6.
Still 6.
And for each of those 216 outcomes, how many ways can this one come up?
Still
6.
6.
And it keeps going.
I thought you were
There's
just
10
gonna
of
keep
those
going.
add times.
And it's absolutely massive.
That is really big.
Right. I can't do my 6s like I can do my 2s.
Really?
Yeah. 2s are easy. So
What's 2 to the 10?
2 to the 10 is 1024. But
2 to the 20.
so if you do 2 to, let's do something crazy like 2 to the 60, I don't know, 5?
Sure.
Something like that.
You probably memorized that number.
I didn't memorize that number. But I can tell you that 2 to 65 is going to be approximately 3, 2, and then, let's lower this because I'm going to run out of space. 3. And then 0, 0, 0, 0, 0, 0, 0, 0, 0. It'll be approximately that. 32 billion. Go ahead and check it.
Hey Siri, what's 2 to the power of 35? 34 million. 34 billion.
34 billion.
No, you got it wrong.
You
So that'd be approximately 32 billion.
billion off.
Yeah.
That's
The
not
approximation
that
gets
much.
worse and worse with bigger and
That
bigger
much.
numbers.
It's not like 2 billion is very much.
It's a quick way to get an estimate for what the numbers should come out to.
So my answers on the test, they're just estimates. If I'm 2 billion off.
Dude,
And you
Well,
still
all the
miss.
other
The difference
numbers were
between-
zeros
the
either.
difference between 3 million and 3 billion is just a couple zeros. Which is pretty much nothing, so
Alright,
it's actually not that far apart.
so here's our S. What's our probability of each little s then? A probability of a particular outcome.
1 over 6 to 10.
1 over 6 to the 10, right?
No.
That's probability of each particular roll.
Yes.
That is the odds that I will roll a 1 10 times in a row.
Oh, okay.
It's stupid small. You're not going to roll a 1 10 times in a row.
Yeah. Not any other number.
Right? Well, when you roll the dice 10 times in a row, you're going to get one of those outcomes. So whatever the outcome was that you end up getting, there was always a stupid small chance of you getting that outcome.
If you look at the world record for the same number rolled on the dice in a row.
You should play Risk with Robert. He's really good at getting 6s.
Oh, yeah.
Well, this is rolling a 1 6 times in a row. It's not rolling a particular number 10 times in a row.
Number.
That's 6 times
This
more
is all
likely.
the different combinations.
That's just one particular outcome. That's the odds of rolling that. Or it's the odds of rolling that. Right? One particular outcome. Okay, so now let's see what I asked you to do. A is the event that we don't rule a 1. None of them are a 1.
Okay.
Right?
Alright.
So that's
So A is going to be the event, no 1s.
Okay.
So now what's the size of A equal to?
6 over 6.
What?
5, 6, 10.
5 to the 10. Because if you can't use a 1, how many options do you have for what your first roll was?
9. I'm not looking at 5.
5. And how many options do you have for what your second roll could have been?
5.
And your third, and your fourth, and your fifth. And so for all 10 rolls, it's 5 options. 5 times 5 times 5, 10 times, 5 to 10. Perfect. So now, what is the probability that you don't roll a 1?
5 to 10 or 6 to 10.
5 to 10 over 6 to 10. Okay, what do you think?
5, 6.
So it comes out 5, 6, right?
No.
No.
That's not how math works.
So this is equal to 5, 6.
Easy.
So it's
No.
almost guaranteed that you won't roll a 1.
No.
No,
Of course not.
of course not. Let's do a quick sanity check to make sure we don't try anything crazy like
Yeah,
that.
that sounds like
If we do 1 to the 10 over 2 to the 10, this is not equal to 1/2. No, it's equal to, 1 to 10 is just 1 over 1024. That is not 1/2.
close.
So don't try any canceling out like that. It's 5 to the 10 over 6 to the 10, or another way you can think about it if you want, is 5/6 to the 10. Same thing. Right? What do you think? What do you think approximately that number is?
A lot.
Do you think it's close to 50%, close to 90%, close to 20%,
Close to 90%.
close to 90%?
Close
Plug it
to
in, Debbie.
6%.
That's 5, 6 to the
Like,
10.
won't roll a 1.
I think closer to
96%.
He said
Ask your phone real quick.
Oh.
Say, what's 5, 6 to the 10?
Hey Siri, what's 5, 6 to the power of 10?
96%.
Oh, whoops, I did it wrong. Hey Siri, what is 5, 6 to the power of 10? It's a decimal.
Yeah, tell me the number.
0.16315.
0, 1, 6, da 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 da, so close to 2%.
Guys, here, 1, 6.
What the earth?
The odds of you going 10 straight times and not getting a 1 is actually pretty small.
Why is that so small?
That's tiny.
Oh, 5, 6 means
It's like 1%.
How?
We make each other smaller somehow.
Oh, 'cause-
When you take a number less than 1 and you raise it to some power,
It
right.
makes it way smaller.
then it makes it way smaller.
But it's supposed to be 10%, is it not?
2%.
10%? Didn't you say 0.016?
I thought it was 0.1.
Was it 10? Was it 16%?
It was 0, yeah.
Oh, what did I say? 16.
Huh.
16%.
I can check again. Hey Siri,
Yeah.
That just doesn't make any sense.
what is 5, 6 to the power of 10? Oh my gosh, it keeps saying, hey Siri, what is 5, 6 to the power of 10? Yeah, 0.161.
0.16.
16%.
Okay, 16% chance.
2% sounds wrong.
Yeah, it did seem small.
Seems way too big.
What?
16 sounds big though.
The odds of going without
Wait,
a 1.
you can
The odds of going without a 1 10 times. I mean, playing the odds at once, you come up once every 6 rolls.
Yeah.
So it shouldn't be that crazy that you beat it for a streak of 10. Unlikely, but should be insane.
Well, I mean, it has.
Anyways, so that's that. So now, let's ask a different question. What's the probability that in 10 tries you get at least 1 1?
Like 100%?
Like 100%, right?
Oh, what, 60%?
What is it?
The opposite of 16%.
The opposite of 16%.
100 minus.
If this is the odds that you never get a
So
1,
84%
then the odds that you get at least 1 1
is a
are going to be 0.84, roughly. Right?
roughly.
Just give or take 2.
So if the probability of A comes out to some number, how many of you have seen this? Have we gone over that?
Complement
The complement? We talked about that?
Yeah.
in logic.
College algebra.
We did talk about that.
So this is a complement symbol. It means everything not in A.
I think we might have.
Oh, yeah, we did go over that in that class.
We did go over
Remember
this
it.
in this
No,
class.
we didn't.
Remember it.
You
Yes,
were
we did.
asleep.
I don't know where else
No,
Debbie
it
would have
wasn't.
seen it.
I don't remember it.
It's literally in our homework, guys.
No, it's not.
All over.
I
Do you
think
read
this.
the textbook?
Yeah, there,
I think she's right. I think we did go
we
over it.
went over it.
We did.
I think she was right.
Alright, so A complement, it's everything not in A.
Have you ever seen that?
Guys, it's
Alright,
Did you
it just
know
means
we-
everything not in this set.
Okay.
So if A was the event, you rolled, or A is the event we didn't roll a 1, then A complement is the event that we rolled at least 1 1. Right?
Yeah.
So if the probability of A is equal to that, the probability of A complement is always equal to 1 minus the probability of A. The probability of getting not A is equal to 1 minus the probability of getting A. Make sense?
Yeah, that's fair.
Okay. Went over that. Okay, 4 of a kind with poker. Let's see if you guys can do this one.
4 of 10?
Yeah, so we're talking about poker hands. So S is going to be the set of all possible poker hands. So what's a possible poker hand that you can have?
Ace.
You can
King,
have
queen, joker.
the ace of hearts with the 2 of spades with the 4 of diamonds
And
with the 3 of spades.
Clubs.
Okay, there's one possible hand.
Isn't it 5?
Did I only write 4 things?
Yeah.
6 of clubs.
6 of clubs. Okay. So there's one possible poker
That
hand.
looks confusing.
You just dot dot dot.
This should be sets, because the order doesn't matter here. So a poker hand is a set of 5 cards, right?
Order does not
True.
matter.
Order doesn't matter in a poker hand. So if I were to swap the position of those 2 things, it wouldn't change my poker hand.
Yeah,
So this is a set, not a list. So S is the set of all possible poker hands. A poker hand is going to be a set of 5 cards. Okay, so that's what S is. First thing we need is the size of S. How many possible poker hands are there? We
50.
talked about this last week.
52, choose 5.
52, choose 5. Perfect.
Choose
52,
Because you
choose
5 out of the deck.
5. There's 52 cards in the deck. Choose 5 of them to be in your hand. Since order doesn't matter, it's 52, 52 choose 5.
Okay.
Make sense?
Yep.
So, what's the probability of you getting any particular hand?
52.
What's the probability of little s?
52.
1 over
5.
52, choose 5.
1 over 52 choose 5. And you know how to calculate 52 choose 5, whatever it is, right?
Yep.
Ninth way.
Everyone know how to use that in the formula?
52 minus 5.
Hey, Siri.
Yeah, so you can also just plug it in. 52 choose 5.
So it's like 2 factorial times 52 factorial.
It's going to be 52 factorial over, what's 52 minus 5?
43.
47.
47
Oh, that's a 5. I was thinking I was a 2.
factorial times 5 factorial. Right? Now, it's 52 factorial. Sorry. There's what it is. Now, 52 factorial is going to cancel out with plus 47 factorial, leaving 52 times 51 times 50 times 49 times 48, and then divide that by 120, and that's how many possible poker hands there are.
Wow.
So we can figure that out if we need to.
Ooh, gamble.
But some big number. Okay, so there is the number of possible hands. Now we want to know what are the odds that you get 4 of a kind. You know what 4 of a kind is? 4 of a kind means you have like 4 threes.
You have the entire.
Okay.
You have an entire rank. There's rank and suit.
Suit, what?
Yeah.
Rank is ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king.
Oh,
That's rank.
I've never heard rank.
Suit is heart, diamond, club, spades.
Well, you have the entire suit for a rank. No. Yeah.
There's only... Okay. So 4 of a kind means you have, out of your 5 cards, 4 of them are the same rank. Right?
Mhm.
Yep.
So, let's say that A is, you have 4 of a kind. What's the size of A equal to? How many ways can you get 4 of a kind?
A lot. There's.
A little.
So you have a hand of 5 cards.
Well, there's 13, isn't there?
There's 13.
There's 13 ways that we can decide which you're going to have 4 of a kind of.
So 13 over 52 of 5. Choose
No.
5.
Almost. So there's 13 possible ranks to choose from, right? You can either have the 4 aces or the 4 twos or the 4 threes all the way up to the 4 kings. There's 13 ways to choose that.
Yeah.
Oh, so it's just 13.
And then
So there's 13 ways to choose your rank.
13 times 5.
So let's just look at my first card. If my first card is going to determine my rank, there's 13 ways I can pick my first card, right?
That's true.
Now, these next cards, there's only one way I can pick them, because they have to all have the same rank as that
Yeah,
thing.
13 times 5.
But now I have one more card in my hand, right?
Yes.
If I have 4 of a kind, it's possible that I have 4 twos and then the 4 of hearts.
Yes.
That's 4 of a kind. It's possible that I have the 4 twos and then the queen of spades.
So that's all.
That's 4 of a kind. How many ways can I pick that last card?
48.
48. Right?
Oh, yeah.
Theoretically, yeah.
Oh.
48.
Yeah. Why'd you write 13?
That's your rank. There's
Chance
13
to
ranks
get a rank.
in a deck of cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. There's 13 ranks.
13 times 40.
So 13 is choosing your rank. Once you know your rank, your other 3 cards are already determined.
I see that.
If you choose your rank is going to be 3, so choose your rank is going to be 3, then all these 4 cards, there's only 13 ways to choose them. Or there's only one way to choose them after that.
Yeah, because you already know it, yeah.
So you choose your rank, there's 13 ways that you can choose your rank. Once you choose your rank, grab those 4 cards. Now you need to choose the remaining card in your hand.
Which is out of 48, yeah.
And since you already took the 4 of whatever your rank was, there's only 48 cards remaining for you to choose from. Everyone understand how it's 13 times 48?
Mm-hmm.
You can now calculate the odds of certain poker hands.
Mm-hmm.
So this is 13 times 48. So now, what's the probability of getting 4 of a kind?
13 times 48 over 52 is 5.
Right, 13 times 48, all over 52 factorial over 47 factorial
Right.
times 5 factorial.
That's 5.
Should we try simplifying this one a little bit?
Yeah.
13 times 48 all over, the 47 factorial is going to cancel out with this, leaving the 52 times 51 times 50 times 49 times 48. And then this is all going to be over 120, right?
Yeah.
You can cancel out the 48 here with the 48 there. The denominator goes into the numerator. So this is 1/3, this is 13 times 120, all over 52 times 51 times 50 times 49. Right? Should we do more canceling out?
Why not?
Doesn't
Or we could just
52 and 13 go to each other? 13 times 3.
Yes. So we can do 13 and 52 leaves us 4 right there, right?
Really?
Yeah. 13 times 4 is 52. A deck of cards, there's 52 cards in your deck.
That's right.
4 of each of the 13 ranks. We can cross out a 5 here, leaving a 10. Taking 5 out of 120 leaves me with what?
4 times 3 times 2, which is 24.
24. So far we have 24 all over. I'll combine the 4 and the 10 here for 40. So we have
Well, you could take 4 off.
51 times 49 times 40. Good so far?
Yeah.
Alright. We can take the 4 out of each of these, which would leave us a 6 up here. And then that's a 10 there. We'll combine it with that. So we have 51 times 490. And so now it's a number you can easily calculate.
So,
Calculator.
51.
6 divided by 51 times 49 in parentheses. Or however you do it.
6 divided by. What's the numbers?
51 times 490.
24,990. No. 0.00024.
0.00024.
Yes.
That's the probability of getting.
That's the probability of you being dealt 4 of a kind.
Oh, being dealt.
You should calculate a pair. Just to see if that's above 50% or not.
Well, you can do this to calculate whatever you want. Now you know how, right?
Right.
Right.
Fine.
So have fun with it. Calculate whatever you want. That's a good exercise. Try and figure out what the odds of getting a pair are. But let's us keep moving with this. All right, scenario. You know that someone has 4 kids.
Okay.
What's more likely? That they have 3 kids of one gender and 1 of the opposite, or that they have exactly half boys, half girls?
Depends on who they are.
Half and half.
Yeah, what's more likely? That they have half and half boys, half girls, or that they have 3 of one gender and 1 of the opposite gender?
Half and half.
Half and half should be, but 3.
Half and half should be.
Probably a trick question.
3 of 1.
No, half and half is.
3 of 1's would be the answer, but half and half makes sense.
So let's calculate it. We can figure this out. So S is going to be the set of all the possible ways that a girl can have 4 babies, right? She could have had
Assuming she's a girl.
boy, she had babies. Boy, all the way to girl. Sorry. I looked at the 6s right there. I just drew 6. Girl. Okay. What's the size of S? How many possible ways can a girl have 4 babies?
2 to the 4.
2 to the 4, which is
2 to the 4. Fantastic. Which is,
16.
wait, not 287?
That's a good guess.
512.
Ah. Okay.
7.
That's odd.
Yeah, it's odd.
I thought your guys' answers were pretty odd. Okay. There's the size of S.
I'm tired.
Now, we need to calculate. Let's do the easy one first. Half boys, half girls. So we'll call that set B. B is half and half. What's the size of B?
It's 2.
1/2 and half.
How many ways can she have 2 girls and 2 boys?
2 girls and 2 boys.
Yes.
1.
1,
4.
Oh,
Okay.
hang on.
8.
3, 4,
2,
That's what I got to.
1,
5,
1.
6.
6.
How'd you get 6?
You were doing this.
You were wrong.
Ah. You have 4 kids. You need to
there's
choose
6.
2 of them to be boys.
I can think of all 6.
Oh,
What?
You have 4 kids. You need to choose 2 of them to be boys. Because if you choose 2 of them to be boys, the rest have to be girls.
Oh, 4 choose
Yeah.
2.
4 choose 2. You have 4 kids. Choose 2 of them to be boys. What's that equal to?
12 over 2.
2 to the thing times 2 to
12 over 2, which is
6.
6. What? Miss whatever you said.
It is totally 2. That makes sense.
It's 12 over 2.
You are right.
It's going to be 4 times 3 over 2 factorial. Is the simplest way to think about it.
4 times, yeah, that's right.
But whatever, however you think about it, the answer's 6. Okay, now let's do the size of A. Size of A is a 1 to 3 ratio in genders.
Alright.
So what's the size of A? So A is I have 3 boys and 1 girl, or I have 1 boy and 3 girls.
So 4 choose 1.
So it's 4 choose. Let's think about choosing in terms of the boys, so that we can be consistent. So I can have 4 kids and choose 1 of them to be a boy, or I can have 4 kids and choose 3 of them to be a boy.
Oh. So now that's bigger.
So it's both those cases,
2. Okay, I see.
right? If she only has 1 boy, then she has 3 of one gender and 1 of the other. If she has 3 boys, then she has 3 of one gender, 1 of the other. Right?
Yeah.
So what is 4 choose 1?
4.
4. How'd you do that so fast?
Mental math.
4 choose 1 is always 4.
Because 4 choose 1 is always 4. Keep in mind what fundamentally this question answers. How many 1-element subsets can you create out of a 4-element set? 4. That's what the choose notation was built to count. Okay. So, and then what's 4 choose 3?
6.
4 choose 3 is the same as 4 choose 1. If you choose 3, that's choosing 1 to leave behind.
So it's 8 options.
So 4 choose 1 is 4, and 4 choose 3 is 4.
That's right.
And these are ones that we think about the answer to without using a formula. You remember what the math represents. How many 1-element subsets can I create from a 4-element set? Just 4. I can pick the first element, or the second, or the third, or the fourth. How many 3-element subsets can I create from a 4-element set? Just 4. I can choose to leave behind the first element, or the second, or the third, or the fourth. And 4 plus 4 is
8.
8. So there's more ways that this happens than this happens.
I was right.
That was 2.
So you're more likely to have your kids spread across the genders unequally than to have them equally distributed across the genders.
Only if you have 4 kids.
That's weird.
If you have 4 kids.
Is it the same thing with like 6 kids?
Well, you can calculate with 6 kids if you want and see, but you gotta see what you care about. Because also keep in mind that having an unequal split, we would also need to. Alright, yeah, we can close the door, make sure the heat's on. But it's nice and cool.
It is.
It turned into like a refrigerator.
For a little. When power goes out permanently, we're so screwed.
Anyways,
Well, we would just start
Okay, we paid tuition.
alright, the power's back on. We're okay. Now, back to this.
Oh, I can see the board. You're writing numbers?
And some letters.
Oh, that's a 3?
That, hopefully, I don't know, where's my 3? That. Alright. So, there's a 50% chance that you're going to have your kids that way if you have 4 kids.
Dang.
Yeah, there is.
Make sense?
Yes.
Not very intuitive. Something you got to think about to get it. Alright, let's see. The same birthday problem. Let's do the same birthday problem.
People having the same birthday?
Yeah, there's a problem.
When's your birthday?
February 27th.
When's your birthday?
September 10th.
When's your birthday?
June.
When's your birthday?
July 23rd.
When's your birthday?
December
And mine's November 10th. None of us have the same birthday.
Dang.
What?
What?
The heck?
That was crazy. What were the odds that none of us had the same birthday?
Let's calculate.
That's a cool thought.
Let's calculate it. What are the odds that none of us have the same birthday? So there's 6 of us. What are the odds that none of us had the same birthday? Let's go over them.
Okay.
Is there
be
a
the
specific
same.
birthday?
Not quite.
Are we doing just by days or by minutes or by seconds?
Birthday.
Or by hours?
Yeah, it's in the title. But we are going to ignore
Birthday
leap years.
could include when they were born on that day.
No, birthday.
For example, let's say you share my birthday. but I
1,
was
2,
born
3, 4,
And
5,
we share
6.
the same birthday.
So we started with Chandler. Now Chandler could have his birthday on how many possible days?
365.
365. There's 365 days that you could have possibly had his birthday on.
Or
Depending
6,
on the year.
366.
When it says born a leap year.
I already said we're ignoring leap years.
Okay.
Okay. So now we go to Chandler. If you know Chandler's birthday, or if we go to Jeremy, if you know Jeremy's birthday is not on Chandler's birthday, if you know that they're different, how many days could his birthday possibly be on?
364.
364.
So it's 300.
Now, if we know what Phoenix's is different than theirs, how many ways can his be?
363.
363, then Debbie would be 362, then Hayden would be 361, then me would be 360. So this is how many ways we could all have our birthdays differently.
Okay.
So if event A is we don't have the same birthdays, none of us have the same birthdays, then the size of A is equal to this product. This times this times this times this times this. You with me? Now what was the probability then? The probability that none of us had the same birthday.
365 choose 6.
it's going to be each of these divided by 365 to the power of 6.
Oh.
Right?
No. Power of 6. Why?
So
Because that's total.
the odds of him having a particular birthday is what? 1 in 365. The odds of me having a particular birthday is 1 in 365. Right? Same with all of us. So how many different ways can we all have our birthdays? 365 to 6.
Yeah.
Okay.
Right? The size of A is this product.
Okay.
So our S, the size of our S is right here.
Okay, there we go.
Oh, so is it just 360?
The ways that we can all have different birthdays is 365 to 6, ignoring leap years.
That's
Okay.
true.
Right? That's the size of S.
Okay.
Okay. The probability then of A, of us all having different birthdays, is the size of A over the size of S. So it's 365 times 364 times times
360.
360 all over 365 to the 6, which is the same as dividing each of these by 365.
But what happens if you get 366 people in a room and you want to see the odds of them all having different birthdays?
So we get 366 people in a room. If we have let's make the problem simpler for you first. Let's say that I have a bag of marbles, and there's only 5 colors of marbles in the bag:
Okay.
red, white, pink, blue, yellow.
There's only 4.
And I have each of us grab a marble. What are the odds that none of us grab the same color?
0.
0. There's only 5 colors in the bag. If 6 of us each grab a color out,
So if you get 366 people in a room,
then 2 of them for sure have the same birthday.
At least.
Yeah.
It's a 100% chance that at least 2 of them have the same birthday. Yes. Make sense? Okay. Now back to this problem that we were thinking about. 365 times 364 all the way down to 360 over 365 to 6. Well, that's basically just, that is 365 over 365 times 364 over 365 times this over 360 times that times that times that all over 365. This is basically one. This is exactly 1. This is basically 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 1.
So 5, 6.
And 1 times 1 times 1 times 1 times 1 is basically
1.
1. So that we expect this product to come out close to 1 or 100%. It is very likely that we didn't all have the same birthday. That is very likely.
But we didn't all have the same.
That all of us had different birthdays. Is that very likely or very unlikely?
very likely.
Very likely. Right?
Okay.
Does it not make sense that it's very likely?
It does.
Well, very likely, just not that close to 100.
Well, we can calculate exactly what it is. I still have my calculator here. Force me to use the web.
Oh, wow.
So we have 365 times 364 times 363 times 362 times 361 times 360. Is that where I stopped? Okay, get some massive number. And then we're going to take all that and we're going to divide it by 360 to the 6. 365 to 6. Here we get 96%.
Oh,
That's
96.
Yeah.
Alright, but
So there's 4% chance that all of us had the exact same birthday.
No, that,
No, there was a 4% chance that 2 of us had the same birthday.
at least.
Okay.
At least 2.
What? That's crazy.
That's pretty high.
So
that seems right.
let's think about it for like a bigger number now. So what if we had like 23 people in this room? What do you think the probability of 2 people having the same birthday then would be?
That except 23 times.
Yeah, but roughly what do you think it would be? Do you think we're talking about like 80%? Do you think we're talking about like 20%? Do you think we're talking about...
73%.
We're having the same birthday.
74.
Yeah, so if I had a room
70.
full of 23 people, and I said, hey, what are the odds that two of us have the same birthday in this room? What do you think it is, roughly?
75.
70.
He said 75. You said what?
40.
What?
Oh.
You took it from 96 to 40?
Actually, I might want to go.
Oh.
Yeah.
It's the other way around.
There's no way it's that much.
How many people have
Compare
the same
23 to
birthday?
300.
Yeah,
You
20 to
said
40.
70.
Compare 23 to 365. There's still a lot of room.
It's just...
Exactly.
Let's make sure we're all answering the same question. I have 23 people in this room. What are the odds that no two people have the same birthday?
That no two people.
That no two people have the same birthday. So with 6 people,
365, so-
with 6 people, the odds were 96% chance.
Oh, yeah, it's gonna be like 70.
Six.
With
75.
23 people, what do you think the odds are roughly?
60.
We got 60.
70,
70, 75.
It's probably lower than
78.
78? And the answer is 50.
50?
50.
Yeah.
There's a 50% chance.
Why'd you choose 23?
Because that's the number that may come out to 50.
Oh, yeah.
So I found the number that would make it come out to 50%. And so this is a common trick that you see like shows when someone's trying to pretend that, oh, they can sense certain things, and so they'll be standing on the stage and there'll be a row with like 40 people on it, and they'll say something like, I'm sensing 2 people on this row have the same birthday. And then they have them go down and list their birthdays, and sure enough, most of the time, 2 of them have the same birthday, because with 40 people, it's pretty likely that 2 of them will have the same birthday.
Yeah, that's like 25%.
That's so weird.
That's the dumbest thing.
That does not
That's
make
like
sense.
going into
Right.
the chapel, like say the chapel's completely full, and saying I'm sensing that two people in here have the same birthday.
Well,
Right.
It's like, well, duh.
Well done. Except for that's a much bigger. Yeah.
But that's only 400.
400. It's 100% chance. At least.
With 400 people, yeah, you get a 100% chance.
Yeah.
Anyways,
That is.
so that's called the birthday problem, common problem.
That's why it's well, duh.
There's your birthday problem.
These time out 40.
That's so weird to think about.
Doesn't make sense at all. 32 compared to 365.
Hmm?
23 compared to 365.
Imagine how
It's like
embarrassing that would be.
1/10.
Pull up 40 people.
Less than
I'm
1/10.
sensing 2 of you have the same birthday.
Every person you add, you multiply by a smaller fraction.
He's like,
He's like, just kidding. I quit.
I'm in the back row.
So the first person doesn't change the ratio. The second person lowers the ratio. The third person lowers the ratio twice as much as the first person did.
23rd person knows a lot.
Right. So that's why it has a disproportionate effect.
I wonder what that looks like on
Yeah, you could graph it.
I know, right?
Okay.
Why'd you wonder?
It would be like,
Yeah. Now the shape of that would be it'd never go back up. It would be constantly be falling down. But yeah, what that would look like, I think that's interesting.
it wouldn't be a harsh draw, but it wouldn't be.
It would be a hard
It's
draw.
a big arch
If it started to go
Yeah.
divided by 2, each one would be big time.
Well, yeah, but then what happens? 23 is 50. What happens when you get to 100?
24 is 23 is 50. 24 would be down there.
What about
25?
Where would 100 be?
It'll just be at the bottom.
It can't be. He's got a good point. Because at 300, there's still something.
So it'd be
So it
literally-
tapers out. So he's right, it's going to be something. Right, it is an interesting question. I've never thought to graph that before. I want to graph it now. So yeah, I'll have to go do that.
Wait, Tony,
Go ahead.
would there be a way to calculate how many times the 13th day of a month would fall on Friday?
That actually would be something I want to do too.
The 13th day of a month will fall on Friday.
Should we
So
just
Friday-
make
There's
that
a
one
1 in 7 chance.
Yeah, let's just take over the problem first.
There's a 1 in 7 chance.
Like how many times it will happen in a year?
The expected number of times will be 2, but 1 is not unreasonable. It's just 1/7
That would be very
for each month.
very difficult to prove.
That was gonna be a point.
Yeah, me too. That was
1/7 makes sense though.
We should
Right.
calculate
I mean, it makes sense.
the odds of a roller coaster crashing.
How do you calculate that?
Yeah, that requires you to know all sorts of things about the particular roller coaster, the materials it's being made of. That one's through the air.
And the people in it.
I mean, people who have taken physics know how hard it is to talk about this object falling if we just include air resistance.
Yeah, that's awesome.
We have not done
Right. You just include air resistance and your physics pulls up. It gets a lot harder. Then you instantly need differential equations. So, you talk about real world phenomena, really quick you need differential equations. Differential equations describe real world phenomena. You need for everything.
Oh, we should calculate names.
Calculate names.
Well, that would
Yeah,
take
just-
thousands of years.
What does that even mean?
Alright.
I mean, just
The
like birthdays,
probability
but
of people
names.
having the same name.
Okay, let's move on.
There's not enough names.
There's another
There's
one.
not-
There's too many.
There's not enough names for that.
We don't, we don't know enough names.
There's also not enough names.
Alright, moving on. Quick proof now. Proof. If A and B are events in the sample space SP, then the probability of A plus the probability of B is equal to the probability of A union B plus the probability of A intersect B. First off, what does that formula look like?
The one
Like
we
the
did
classroom
before,
one?
where it's teacher A plus B. Oh, absolute value one.
Yeah, the size of A plus the size of B is equal to the size of A union B plus the size of A intersect B, right?
Crazy how similar that is.
It's like the same thing.
You remember this formula? We went over that 100 times.
Yes.
You see how this is almost the same thing as this?
No?
Yes.
Yeah.
Look at it.
Yes.
Yes.
It's the exact same thing except for instead of the size, it's just the probability.
Right, but now it's a probability of A. And intuitively, probability of A is typically going to be something like the size of A over the size of S. And the probability of B is going to be the size of B over the size of S. And the probability of A union B is going to be the size of A union B over the size of S. And the probability of A intersect B is going to be the size of A intersect B over S. So going from this formula to this formula in most cases is just dividing everything by the size of S.
Okay.
That's typically what it is. Now your formulas don't have to be evenly distributed. They don't have to be, you don't have to have evenly distributed probabilities, so that doesn't quite prove it. That just handles a special case, which is a case that comes up the most. So the way to see that this is always true is to start with 1, let little s be anything in our set of possible outcomes.
All right.
So here's the way that, remember what P of A is. Let's understand exactly what the definition of the probability of A is. It's the sum of all the little a's and big A's of its particular probability. So this is just a sum of a bunch of probabilities. This is just a sum of a bunch of probabilities. This is just a sum of a bunch of probabilities. This is just a sum of a bunch of probabilities, right? That's what each of these are. So what I'm going to do is to show that these two things are equal, is I'm going to show that the exact same terms are being added to both sides of the equation no matter what. And if both sides of the equations are adding up the exact same terms, then they're obviously equal. Make sense? So I'm going to grab a particular little s that these terms may or may not include when they're calculating the probability of. Now we have 4 possible cases. We have 4 cases for how little s is distributed amongst A and B. S can be an event A and B. It can be in just A, it can be in just B, or it can be in neither. Make sense? So we have 4 cases. If S is in A and B, comma, then the probability of little s shows up on both sides twice. It's going to show up here, it's going to show up here, it's going to show up here, and it's going to show up here. Right?
Okay.
If little s is in A and B, then when you calculate the probability of big A, one of its terms is going to be the probability of little s. That's going to be one of the things that you were adding up. Does that make sense? Same with the probability of B, same with the probability of A union B, same with the probability of A intersect B. So this little s would show up in that case on both sides of the sum twice, exactly twice. That's one possible scenario. If s is in A and s is not in B, then it shows up on each side what?
Once.
Then it shows up on each side once. If it's in A and not B, it shows up here, it doesn't show up here, it shows up here, and it doesn't show up here. If it's in A, but it's not in B, is it in the intersection of A and B?
No.
What do you think? Why not?
I don't know.
You don't know. Let's make sure we're understanding this. So let's try out a set A. Let's try out a set B. Here's event A, here's event B. And they could have some things in common. Event A could be, imagine we're rolling two dice. Event A could be, I rolled an even. Event B could be, I rolled higher than a 5. Are there even rolls that are higher than a 5?
Yeah.
Yeah, like a 3-3. If I roll a 3-3, that's higher than 5, and it's even. So our events can overlap. That makes perfect sense, right? So now if we know our particular outcome is something that shows up in A but not in B. So maybe I roll a 1-1. It's even, but it's not higher than 5, so it's just in A. You with me? So if it's just in A and it's not in B, is it going to be in A union B? If I union those two sets together, remember which one union is? If I union two sets together, we take everything in both sets. So if little s is just in A, is it in A union B?
Oh, yeah.
Yes. What about their intersection? Where's the intersection of A and B? That's just this space right here. Is it in their intersection? No. So if little s is just in A and not in B, then it's going to show up in the probability of A. It's not going to show up in the probability of B. It's going to show up in the probability of A union B, and it's not going to show up in the probability of A intersect B. Right? So it showed up here, and it showed up here. So it's a term that showed up on both sides of our equation once. So they'll cancel out. They'll be equal. I'm showing that we're adding up the exact same numbers here that we're adding up here, and therefore these will always be equal. Because for each of the numbers that we're adding up, either for each of the probabilities that we're adding up, it's going to be an event that shows up in one of 4 ways. It's going to be an event that shows up here, just in A. It's going to be an event that shows up here, in both A and B. It's going to be an event that shows up just in B, or it's going to be an event that's not in A or B. Like in our case, we were talking about if I roll a 1-2. That's not even, and it's not greater than 5. Those are our 4 possible cases. I'm showing that no matter what little s is, no matter how it lands, it shows up on both sides of this equation the same way. Therefore, this equation is always equal. That's what we're showing. So here, if s was in both A and B, if little s was right here, then it shows up here, it shows up here, so it showed up on this side twice. It shows up here, and it shows up here, so it shows up on this side twice. If it's just over here, it shows up here, it doesn't show up here. It shows up here, it doesn't show up here. If it shows up here, then not here, yes here, not here. So it shows up on both sides once. Finally, if it's out here, then it doesn't show up here, doesn't show up here, doesn't show up here, doesn't show up here. So no matter what, it shows up on both sides of the equation the same number of times, so this equation is always true. Make sense? Okay. So now let's move on to some properties. Just some stuff that's hopefully intuitive now. What about if A and B have an empty intersection? So here's event A, here's event B. Event A might be I rolled less than a 4. Event B might be I rolled higher than a 6. It's impossible for me to roll both less than a 4 and greater than a 6. That's impossible, right? So that's an example of where A and B's intersection is the empty set. So if A and B's intersection is the empty set, then what is the probability of A plus the probability of B equal to?
A union B.
It's just equal to the probability of A union B. Because what's the probability of A intersect B? 0%. What is the probability of my S being in both A and B? Of an outcome being in both A and B? 0%. So if your intersection is empty, then your probability of A plus your probability of B is equal to your probability of A union B plus 0. Make sense? So if your intersection is empty, this formula holds. Special case of this. Next one. In general, so let me rewrite this equation here, but just change the order that we write it. The probability of A union B plus the probability of A intersect B is equal to the probability of A plus the probability of B. Okay, this is always true. Always and forever true. Now, what is the smallest this number right here can be? 0. It doesn't make sense to talk about a probability less than 0, right? So if this number is always 0 or greater than 0, then if I get rid of this term altogether, and we want to keep this expression true, then the probability of A union B has to always be less than or equal to the probability of A plus the probability of B. Because getting rid of this term could have only made this side smaller. Make sense? So that's this inequality. Now, what is the probability of S equal to? Big S now. What is the probability of my outcome space always equal to? What is the probability that my outcome is one of my outcomes?
The size of
100%.
size of A over
100%. Are you guys getting lost? What is S?
Yeah.
We're talking about big S now. This isn't little s, this is big S.
confused on one of the things you wrote. That thing up there where you cross that out.
Yeah? If you know that this is always true, right? We know that that's always true. And then if we get rid of whatever number this is, if we just drop that, that could have only made this side of the equation smaller. Maybe it didn't change it. Maybe this number came out 0. But this number could have also been something like 0.5, right? So, if we get rid of that number, we could have only made this side of the equation smaller.
Okay.
Maybe we didn't change it, so maybe this is equal to this. But maybe we did change it, and so we made it smaller. So this should always hold. The probability of A union B better always be less than or equal to the probability of A plus the probability of B.
My question is, how can it get smaller? Say you have 1, 2, 3.
Because it could have the intersection.
Well, let's say you have 1, 2, 3 in A, and you have A, B, C, and B, and 3 and A intersect. And then when you break off that intersection, then it's just still 1, 2, 3, and A, B, C.
Okay, let's come up with a scenario. Let's say that I've got a bag of little balls that are painted half red, half orange. Okay? And I say, randomly grab a marble ball. And I say, A is the probability, A is the event, your ball has red on it, and B is the event that your ball has orange on it. And all the balls are half red, half orange. What's the probability that your ball was half red or half orange? 100%. What's the probability that your ball was red?
50.
Or that your ball had red?
100%.
100%. What's the probability that your ball had orange?
100%.
100%. Is 1 equal to 1 plus 1?
Close enough.
No. Is it less than or equal to 1 plus 1? Yes. Because the odds of you having a ball that was red or orange, plus the probability of you having a ball that was red and orange,
Oh,
you see?
yeah.
So these event space, it's because A and B can have overlap. Because then when you count the probability of A plus the probability of B, you count the overlap twice when they have overlap. So this over here could end up double counting. And it ends up double counting exactly when there is overlap, which is how it can sometimes come out to over 100%.
Why is there a 100% chance to pull a red one?
Because
No. What are the odds that you pull a ball that has red on? Every ball is exactly half red, half orange.
Oh, the balls are split.
Yes, the
Oh,
ball.
others have
Right.
red, okay.
So, what's the odds that you pull a ball that has red on? 100%. What's the odds that you pull a ball that has orange on? 100%. What's the odds that you pull a ball that has red or orange on it? 100%. What's the odds that you pull a ball that has red and orange on? 100%. So everything was 100%. So 1 plus 1 was equal to 1 plus 1 in that scenario. But up here, we just had 1 was less than or equal to 1 plus 1. Both those are true. I was giving him a case where this number was a positive value and actually changed it. Make sense? Okay. So now, let's set the sample space just to make sure you guys understand this. We're going to set the sample space for flipping a coin once. Right? So it can come up heads or tails. Nice and simple. Now our probability function for each little s is equal to 1/2. Question, what's the probability of big S here happening?
100%.
100%. If my event is the same as S, its probability is 100%. So the probability of big S is always
What?
1. Make sense?
Yeah.
Okay, what's the probability of the empty set if your event includes nothing?
1.
100% also. No, 0%.
What?
I flip a coin. What are the odds I get nothing? Not the odds I get heads, not the odds I get tails. What's the odds I get nothing?
Okay, but if it's the empty set, then
The empty
wouldn't
set
it be
is the
like-
event including nothing.
Then wouldn't it be like if you and you, then you'll get. That's
No,
100%.
because we're still talking about some sample space. So we're still talking about some set like this. So we're still talking about the event, we're still talking about the set of outcomes for flipping a coin. So I say, we flip a coin, here's the set of outcomes, heads or tails. What are the odds that we get? Nothing.
Well, if you land on the very side.
Well, that's still something, and if we're going to include that, then we might put side in here, but that's not nothing. What are the odds that you get nothing?
Yeah.
Okay, always 0%. And then finally, we already talked about this one, but the probability of getting not A is equal to 1 minus the probability of getting A.
We did that before.
Yeah. If there's a 60% chance that you get A, what are the odds that you get not A? 40%.
I'll say it's 16.
Oh, I said
16
60.
was the chance for last time too.
Okay. 60%. Okay. So we understand these 4 properties?
Yeah.
Alright, let's move on now to the next section. Conditional and independent events.
Okay.
Let's move this since all this section's going to be related. I cannot see that. Jeez. Getting a glare from the windows. Look on that. Can you see my hand?
Yes.
Okay, so we can see all this.
Yeah, you can see the line.
Perfect. You have better vision than me. All right. So moving on to conditional and independent events. First, let's give you intuition for this. What are the odds that a particular student is late for school?
Very.
We'll talk about some good student.
Oh.
What are the odds that a good student is late for school? Small, right? Small. What are the odds that your alarm clock breaks? Small. What are the odds that you're late for school given your alarm clock breaks?
100%. 100%.
The only chance.
They'll be even higher.
Let's say this
Very,
again.
very small.
What are the odds that a student's late for school? Small. What are the odds that a student's alarm clock breaks? Small. Now, if you know that a student's alarm clock breaks, what are the odds that they're going to be late for school?
100%. Well,
Not small.
big.
Big. Jeremy, if you were trying to make it to school, and I went and I shut off all your alarm clocks, does that increase the chance that you're going to be late for school?
Yes.
Yes. So if your alarm clock doesn't work, that increases the chance that you're going to be late for school.
What if you're late isn't connected to the alarm clock? What if there's other reasons you're late?
There could be other reasons you're late. But if I know that your alarm clock broke,
There's a higher chance you're
then I now know that there's a much higher chance that you end up late for school.
Okay.
Trying to pick one that's intuitive.
So too small is going to create big.
No, it's just that trying to show you that these things might not be as intuitive as you think. Trying to show you related events. Those we would call not independent events. Your getting to school on time is dependent upon your alarm clock working.
Yeah.
Those two events are somehow related to each other.
They're dependent.
And so even though the odds of you being late to school is small, and the odds of your alarm clock breaking is small, the odds of you being late to school given your alarm clock broke, that's now big.
Okay.
If your alarm clock breaks, then you will be late. Chances are.
It increases the chances. So these are related events. Knowing one somehow tells you about the other. They are not independent events.
Well, the alarm clock breaking is. You being late dependent on
Right.
the alarm clock.
Your being late is not independent of your alarm clock functioning correctly.
But not vice versa.
Right. Doesn't necessarily have to be vice versa. Okay. So that gives you some intuition for it. So even though we're talking about small probabilities for two events, somehow combining them together can give us a big probability. All right. Let's try another one. More direct one that we can calculate. So let SP be a sample space for rolling a pair of dice. So we're rolling two dice. We're going to say A is the event we rolled an 8, and we're going to say B is the event we rolled an even. You with me?
Okay.
So let's just start by talking about rolling an 8. How many ways can you roll an 8 with two dice?
6 to 536.
5.
I
Six,
came up with
yeah.
first. 536.
Or 4.
4.
Wait, what?
7 is 636.
7 is 6.
Yeah, but how do you get just a 1?
So 8 is 4.
Wait, what?
It's an even
Oh,
number.
true.
No, it's 5.
Yeah.
That's what I said the first time. You said no.
Yeah.
Think about it. Don't listen to me. I'm going to lie to you. Can't trust your teachers.
What's the fifth one?
Yeah, what is the 5th one?
We're talking about rolling an 8. You can get 6 and a 2, a 5 and a 3, a 4 and a 4, a 3 and a 5, a 2 and a 6.
3 and 5.
There's 3 and 5, there's 5 and 3.
Oh, you said that.
Then
There's 6 and 2, there's 2 and 6. And then there's 4 and 4 in the middle.
Oh,
4 and 4.
Oh, 4 and 4.
I forgot.
Okay.
4 and 4 and 4.
So there's 5 ways that we can roll an 8. So what are the odds that you roll an 8? If I give you 2 dice, you roll, what are the odds you roll an 8? Huh?
5 out of
36.
36.
5 over 36. Perfect. Okay, you roll 2 dice. What are the odds that you roll an even?
1/2.
50%.
What?
Oh no, it's
Yeah,
two
think
dice.
about
You
it.
can't roll.
You're rolling 2 dice. What are the odds that you roll an even?
8.
30 out of 60 out of 8.
Trying to divide 36 by 2.
Why isn't it 15?
19 of 36.
It's just 1/2. 50%.
It's not.
It is.
That's what he
2
said.
or 12 don't work. I said it first.
For the first die,
That's what I said. You said.
when you roll a single die, what are the odds that it's even or odd?
50.
50-50.
There's more
With the
evens.
single die. With the single die.
Yeah.
So, with each single die, there's a 50% chance that's an odd and a 50% chance that's an even. You with me? Now, an even and an even makes an even, and an odd and an odd makes an even. An odd and an even makes an odd, an even and an odd makes an odd. 2 ways to get even, 2 ways to get odd, each equally likely.
It evens out.
Doesn't. There's 5, 6.
Yeah.
5 odds to 6 evens.
Because you can't get one.
I don't know what you're counting.
Look, you
2,
can't
4,
get one.
6.
Oh, you don't count like that. Doesn't work. Because 7 is more likely than 8.
True.
Weird. Okay.
2 is less likely than 3, but you're going to end in 12. So no, you can't just count the numbers of outcomes that could come up.
So it does end up. I'll take your word.
Well, don't take my word for it.
7 is more
I can see your logic before.
Right.
How the
Should
pairs.
be pretty straightforward. The first die can come up an even or an odd 50% of the time. The second die can come up an even or an odd 50% of the time. Right? If you get even and an even, so you can get even and an even, in which case it's an even. You get odd and odd, in which case it's an even. You can get an even and an odd, in which case it's odd, or you can get an odd and an even, in which case it's odd. 50-50.
Yeah, I saw that.
Okay. So, 1/2. Okay, now this one. What is the probability that you ruled an 8 given that you ruled an even?
118.
Isn't that divides?
Oh, sorry, new symbol. Thank you. New symbol. So you're going to have probability of some event, straight line, some event. The way that you read that is the probability of A given B. So you know B occurred. What's the probability that you got A? So I'm sitting here with 2 dice, and I say, my roll's an even, but I don't show you what my roll is. What are the odds that my roll was an 8?
5.
It could have been a 2, it could have been a 4, it could have been a 6, it could have been an 8, it could have been a 10, it could have been 12.
If you were not.
Yeah, but some of those.
6 over 36.
That's for 7.
1/6.
1/6.
There's a lot
No.
of chances it's an 8.
2, 4, 6, 8.
So you think it's only 6 over 36?
There's 1 out of 5. 1/5.
He says 1/5. Anyone else want to throw out the right answer?
6 over 18.
50%. 1/2.
Oh, 1/6. That's what 6.
We got 1/2 out of somewhere.
1/6.
Still not 1/6. Still haven't heard the right answer.
2, 4, 6, 8, 10, 12.
Yeah, but the probabilities are different.
Yeah, you can't do that.
Probabilities.
Thinking.
8's the most likely other than 6.
5 through
6 and
6.
8 are the same.
Divide by 2. 5 16ths. 5 18ths.
5/18.
I said 6 18ths, I suppose.
The answer is 5/18. Okay,
Makes sense.
let's make sense of it. 5 out of all my possible 36 rolls are an 8. Right?
Yes.
Now let's ignore all my odd rolls. So now I only have even rolls. How many even rolls are there?
18.
18. Half of 36. How many of my even rolls are going to be an 8?
5.
All 5 of my rolls that were going to be an 8 are still going to be in even rolls.
Oh.
So we didn't get rid of any of them when we got rid of our odds. So we have 36 possible rolls. 5 of them give us an 8. I get rid of all the ones that give me an odd. I still have the 5 that give me an 8. How many do I have left? 18. 5 of them are an 8. So 5 over 18.
Yeah.
Okay, let's look at it the other way. What's the probability that I rolled an even given I rolled an 8?
100%.
Wait,
Yeah.
what? Oh.
What is the probability that I rolled an even given I rolled an 8? So I rolled the 2 dice. I say it's an 8.
No, that's.
What are the odds you think it's even?
Well, it depends on who's looking.
I would say 2/32.
100% chance. Okay. Now, pictorially, let's come up with a way to think about these things. So, and let's give a precise definition now. So let A and B be events in some sample space SP where the probability of B is not equal to 0. That's important. Your given thing here, in order for this to make sense, it can't have a probability of 0. Otherwise, it's going to break us. So I can't say, what is the probability that I rolled even given that my dice add up to 157?
Not very high.
When you only roll 2 dice.
Yeah, not very high.
Right, doesn't make sense. Because you can't have had B happen. So this is the probability of A given B. That doesn't make sense to say if it's not possible for B to happen. Make sense? So the probability of B can never be 0. Otherwise this type of thinking doesn't make sense. So let A and B be events in a sample space where the probability of B is not equal to 0. Then the probability of A given B is equal to the probability of A and B divided by the probability of B. Let's pictorially make sense of this. Well, first let's make sense of this just with the one that we just did with here. What is this set A intersect B when we're talking about ruling an even and it's an 8?
5/36 plus 1/2.
A intersect B in that case is what?
Intercept. It's an even.
A is, so we're looking at this one right here. A is we rolled an 8, B is we rolled an even.
So there's 1.
What are you guys talking about?
You can only roll 8 once.
First off, what is a set A?
5.
I think you guys are losing track of the fact that these are sets.
It's 1. So it's just 8.
What is the set A?
Rolled an 8.
Rolled an 8. But what's in there? Tell me what's in here.
Oh, 1 set. 2 5. 2 6.
2, 6.
6 2.
6, 2.
3 5.
3, 5.
5 3.
5, 3.
4 4.
4, 4. Okay, this is A. I think you guys are losing track of the fact that we're talking about sets here.
We're losing that we're talking about 2 different die. That's what I'm losing.
Okay, there's A. What is B? B is all the even rules. There's all our even rules, right? What is A intersect B?
All the rules that are.
All the rules that are even and an 8.
So all day.
It's just A in this case.
All day.
Because everything in A was in B. Okay, so the probability of you given A given B is equal to the probability of A intersect B divided by the probability of B.
Okay.
So the probability of A divided by the probability.
So what was the probability of A intersect B in our scenario?
5 total outcomes.
It was what?
A.
It was 8 to 5.
There were
So
5
what are you
possible.
asking?
What is the probability I rolled an 8?
5 out of 36.
5 out of 36.
5 out of 36. What is the probability that I rolled an 8 and an even?
5.
5 out of 18.
Oh, it's 8.
What is the probability I rolled an 8?
Oh, it's
5 out of
36.
What is the probability I rolled an 8 and an even?
5 out of 36.
It's still just 5 out of
Well, you've
36.
been saying this whole time.
No, you kept saying 5.
Yeah.
I wasn't asking for a size of a set, I was asking for a probability. Okay, so the probability of A intersect B, B, and we're looking at over the probability of B. The probability of A intersect B is equal to 5 out of 36 in our case, right?
Yeah.
What was now the probability of B?
It's still what it was.
What's the probability of me rolling an even?
Is 18.
50%.
1 out of 18.
18 over 36.
18 over 36.
Which cancels out 36. I see that.
Right, but we'll keep it 18 over 36. Right?
Yes.
Now, when you have a fraction divided by a fraction, you multiply by the reciprocal. Right?
Right.
So 5 over 36 divided by 18 over 36 is the same as 5 over 36 times 36 over 18.
Yeah.
Right?
Yeah.
36's go out and you're left with 5 over 18.
And that's what we got. I see that.
And that's what you got.
Yep.
Let's try and get more intuition for how this formula works. So the probability of A given B. So here's my sample space S. Here's A, here's B. With me so far?
Yes.
And their intersection I highlighted.
Right there.
Now the probability that I get A by itself is probably like 1/4. A is probably 1/4 the area of all of S, right? Maybe 1/5.
Okay.
Okay.
You with me? So just looking at the picture, the probability of A is like 1/5. But now, what's the probability of A given that B occurred? So if I know B occurred, then I now know that we are in B somewhere. So if we know B occurred, now what is the probability that we got A?
It's like a half.
It's like a half now. Right?
Yeah.
We're saying what portion of A lied in B?
It's the intersection.
Yeah, it's the intersection. So it's the probability. What is the probability? If I know that B occurred, what's the probability that we were also in A? It's going to be this intersection divided by the size of B. It's going to be what portion of A is there in all of B?
Right.
It's going to be the size of the overlap in B divided by the size of B.
I'm not understanding why it's not just the intersection.
Why it's not just the intersection? The intersection is a probability of both of them happening. So let's draw a picture really quick for the alarm clock student late scenario. Here's the event where the student is late. It's not very likely.
Okay.
Here's the event that their alarm clock broke. Not very likely. What are the odds that a student was late and their alarm clock broke? What are the odds that we end up right here? Not very likely. But if I say, now it's given that your alarm clock broke. So now we know that we're in one of these events.
Oh.
What are the odds that we're also in here?
Like
I see
50%.
that.
And so now it's going to be this area, the highlighted area, divided by the area B. Which now is going to be a big ratio. Does formula make intuitive sense?
It's because of given.
Because of the given. Perfect. Let's do another scenario. Alright, so back to our spinner. Question, what's the probability if I spin that spinner that I get a 1?
Half.
We'll say 50%, right? Just keep it simple. Now I say, what's the probability that I spun a 1 given that I spun an odd?
75.
50.
50. No.
If you already had spun it odd, then it's only.
You know I spun an odd. So I spin my spinner, I don't let you see it. I say, I'll give you a hint. It's odd. What are the odds that I spun a 1?
75.
Yeah, it's gonna be. Well,
Maybe
you're keeping the quantities.
Oh, hang on. 50% divided by 25%. Right? No, divided by
Yeah, you gave us.
12.
So what's A going to be?
A intersect.
A intersect B.
A intersect B is, what is the probability that I spun a 1 and an odd?
It's 50. It's
50% chance, 1/2. What are the odds that I spun a 1 and an odd?
If you spun a 1, then it's
50%.
Spinning a 1 is the exact same thing as spinning a 1 and an odd. There's no difference in this case.
So it's 1.
So that's 1/2.
Yeah. What it was.
1/2. 50% chance that I spin a 1 and an odd. What are the odds that I spin an odd?
There's 1.
it's like 60.
let's keep this over 8. So we'll write this as 4 over 8. Same thing.
It's 62.5.
62.5.
What are the odds that I got an odd on the spinner?
62.5.
5 8.
That works too.
5 8.
It's the same thing, but.
Keep those fractions. Keep your life simple.
Keep eights.
Why 5/8?
That's what 62.5 is.
1 plus 3.
Compare
Where did you get
62.5.
62.5 from?
50% plus 12.5% because that's half true fraction.
Is that what you did?
Yeah.
That's what I did.
That's
But
the same
5/8 and 4/8 is 9.
Look.
That's over 100%.
Forget the formula for a sec. Just focus on the question. What are the odds that I spun an odd number? Look at, break this thing up into 8s. 1, 2, 3, 4, 5 of my 8s are an odd.
Okay.
Make sense? So the odds that I spun an odd are 5 8. The odds that I spun a 1, given that I spun an odd, or sorry, the odds that I spun a 1 and an odd are 4 8, 1/2. Now the probability that I spun a 1, given that I spun an odd, is equal to da 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 da, 8 go out, we're left with 4/5. There are 5, if we break this up into 8s, 5 of those are an odd, 4 of those are a 1. 4 of my 5 ways of getting an odd, if you want to think about that, were a 1. So if you know that I spun an odd, well, 4/5 of my odds are 1.
That was way too simple.
Yeah, that's close.
Pretty straightforward, right?
Yes.
Okay, let's make sure. Now I want to know, what are the odds I spun a 4, probability of 4 given even?
Well, there's 1, 2, 3, 8.
So it's
that's
1/8.
even. And it's 1/8.
3 8s.
No, there's 3 8, so it's 1/3.
1/3.
Yep.
Why not?
1/3 of my evens are 4. Now, let's just do brute force formula.
Formula is fine.
What is the probability that I spun a 4 and an even? 1/8. That's the same as just spinning a 4. Right? What are the probability that I spun an even? 3 8s. 1/8 divided by 3 8s is equal to 1/3.
That was great.
Yes. But I want you to know how to go from the formula to the answer, because it's not always going to be one that you can just stare at the picture and figure it out. So I'm trying to give you ones where the formula is easy so that you know how to use this and think about this way. Hopefully, if you would just stare at the picture, you could have answered the question before we even had the class.
Yeah.
Okay, let's try another one. A coin is tossed 5 times. What are the odds that the first flip was a tails, given that there are exactly 3 heads?
Okay.
So now we did examples of cases where it was dependent. Now I want to show you an independent event. Right? Let's go to the simplest case of an independent event. I flip the coin and it comes up heads. What are the odds that my next flip will now be a heads? I knew that the first flip was a heads. Now I pick up the coin and I flip again. What are the odds that my second flip is going to be a heads?
50%.
Still just 50% chance. Knowing that the first flip was a heads didn't help you in any way. Right?
Yes.
Yes? Okay, so let's look at this. A coin is tossed 5 times. We have 5 coin flips. What are the odds that the first flip was a tails, given that there are exactly 3 heads flipped? So I flip the coin 5 times.
2/5. Or, yeah, 2/5.
Good. I flip a coin 5 times, right? I know that exactly 3 of them are heads. Which means how many of them are tails?
2 out of
2. 2 of the 5 are going to be tails. 3 of them are going to be heads.
Okay.
So, how many ways can we plug in what goes there?
5.
Let's think about a different way. I have 5 flips. I'm going to choose 2 of them to be tails.
No, that's 5 choose 2.
So there's 5 choose 2 ways.
Which is 10.
What?
This is not 10. 5
We
choose
have
2 is 10.
5 coin flips. 2 of them are tails.
5 choose 2.
So 5 choose 2. So there's 5 choose 2 ways that we can possibly have 2 tails. 3 heads, 2 tails. Now, what are the odds that the first one is going to be a tails? Basically, that's still overthinking it. We have 3 H's. You know that we have 3 H's and we have 2 T's. And I've got to fill this out, man. Right?
Okay.
I randomly pick one of those to go first. What are the odds I chose a tails?
2 fifths.
2 fifths. Right?
Yes.
So it's 2 fifths chance that the first flip was a tails. So knowing that there were 3 heads actually gave you information about what the first flip was.
So the answer is 2 fifths.
The answer is 2 fifths.
Why is that so simple?
So simple. All right, let's try another one. A coin is tossed 5 times. What are the odds that the first flip was a heads, given that the last flip was a tails? So now I flip a coin 5 times, and I tell you, don't worry. I'm going to tell you that the last flip was a tails. So now what's the odds that the first flip was a heads?
4 fifths.
4 fifths now.
What?
Because
Is it still the 3 heads?
4 fifths
No.
because it doesn't matter.
New scenario completely. A coin is tossed 5 times.
Oh, yeah.
I have 5 coin flips in front of me, and I don't let you see them. You're trying to guess what my first coin flip was. I tell you that my last flip was a tails. What are the odds that my first flip was a heads or a tails?
So we now know 1/5 was a tail.
It's still just 1/2. Knowing what the last flip was in no way gives you information.
Yeah, okay.
So in that case, it was independent events. Intuitively. Make sense? Okay. Next one. Let A and B be events in some sample space. Then we say that A and B are independent events if and only if the probability of A occurring and B occurring is equal to the probability of A times the probability of B. You're already used to this. If I say, what's the odds that I flip a heads, it's, what's the odds that my first flip, I flip the coin twice. What's the odds that my first flip is a heads?
50%.
50%. What's the odds that my second flip is a heads?
50%.
50%. What's the odds that my first flip is a heads and my second flip is a heads?
1/4.
1/4. The odds that my first flip is a heads and my second flip is a heads is 1/2 times 1/2.
Yeah. With the independent.
Intuitively, you already understand this with independent events.
Okay. Yes.
And the first coin flip obviously doesn't affect what the second one was. That's what we mean by independent.
So in your
They have no effect on each other.
in your title, conditional means dependent. Conditional.
Conditional was what we were doing here. And then independent versus independent is what we're doing here.
Independent versus independent.
Yeah. Dependent means that they're not independent. Independent means just this right here. That the probability of A and B occurring is the same as the probability of A times the probability of B. Now, another way that we can make intuitive sense out of that is with B doesn't give you any information about A occurring. If I told you my second flip was a tails, what are the odds that my first flip was a heads? Knowing that the second flip was a tails doesn't tell you anything about the first flip.
Yeah.
That's another way that you can think about events being independent. So, here's its definition. It's if the probability of A and B is equal to the probability of A times the probability of B. But here's another way that you can think about it. That says the same thing as the probability of A given B is still just the probability of A. Knowing that B occurred doesn't change the probability of A happening.
Yeah, that's true.
Like I said with the coins. What are the odds that my first flip was a heads, given that my second flip was a tails? It's still just a probability that my first flip was a heads. Knowing that the second flip was a tails doesn't change anything. So in that case, the probability that I got a heads on my first flip, given that my second flip was a tails, is still just equal to the probability that I got heads on my first flip. Doesn't change anything. Or, which is the same thing as this. It's the probability of B given A is still equal to the probability of B. If that's the case, then they're independent. Just show you this really quick. If this is true, these are true. We can get that from our definition here. By definition, the probability of A given B, by definition, that's equal to the probability of A intersect B over the probability of B. But now if I know that they're independent events, then I know that the probability of A intersect B is just the probability of A times the probability of B. So I'll substitute that in. So we get the probability of A times the probability of B all over the probability of B,
Probability of A.
which that cancels out, and so you get probability of A. So the probability of A given B is equal to the probability of A. And you can do a similar thing to show that this also falls from that. So this is logically equivalent to this is logically equivalent to this. They say the same thing. So however you want to think about independence, doesn't really matter. Whichever appeals to your intuition better. Okay, next definition. Notice that it got kind of annoying. If I wanted to talk about rolling a die once, and I create my sample space for rolling a die once, so when we rolled a die once, our sample space was S is equal to 1, 2, 3, 4, 5, 6, and P was equal to, P of little s was equal to 1/6 for all little s and big S. So when I created that sample space for just rolling one die, and now if I want to talk about rolling two dice, it's really annoying to have to come up with a completely different sample space. And then maybe I want to talk about rolling 3 dice, or 4 dice, or 5 dice, or 6 dice. I don't want to have to keep coming up with new and new sample spaces for all those scenarios. I want somehow to be able to work off just this base sample space I already set up for rolling a single die. With me so far?
Yeah.
So that's what this enables us to do. So let SP be a sample space like this. And let N be any positive integer. N is in the set of positive integers. And now let S to the N be the set of all the length and lists of S. In other words, S to the N is equal to S cross S cross S cross S cross S N times. Then we call S to the N with P is the n-fold repeated trial sample space where the probability of some list is equal to the probability of the product of each of the items in the list. That seems like a mouthful, seems really complicated, but it's exactly what you would expect it to be. So let's look at, oh, I have an example here. So SP is going to be the sample space for rolling a single die. That's what we have up here. Now from this, I'm going to create a two-fold repeated trial sample space from this sample space right here for rolling 2 dice. So I'm going to show you S to the 2 now, this new sample space that we created. All right, what do we do? What is S to the 2? S to the 2, looking at our definition, S to the N is equal to S cross S cross S cross S N times. If it's S to the 2, then it's just going to be S cross S.
Yep.
So what is going to be in S2?
That's
S cross S, all the ordered pairs of elements from S. All the 2-element lists where we pick elements from S. So it's going to have in here 1, 1, 1, 2, dot, 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 all the way up to 1, 6. How many elements are going to be in, or 6, 6. How many elements are going to be in the list, or in the set?
36.
36. And now, what is the probability of 1, 1? We know it's 1 over 36 from before, but using our definition here, it says the probability of some particular list of outcomes is equal to the product of all the individual outcomes. So we're saying that the probability of 1, 1 is equal to the probability of 1 times the probability of 1.
Which is 1.
Going back up to our probability function, what's the probability of 1?
6.
1, 6. So it's 1, 6 times 1, 6, which is 136. So we're still doing it exactly how you knew before, but now we can just define one sample space and talk about a bunch of different events now, like rolling multiple die. So just to make sure we completely understand this, let's just one more time. This time let's talk about S sub 4. So S and P are still defined right here. We're using this S and this P right here, just to make sure we're all super clear. Here's my S and P. There's my sample space.
Okay.
All right, now let's look at S4. S4, what's in S4?
1, 1, 1, 1.
1, 1, 1, 1.
And 1, 1, 2.
1, 1, 1, 2. And we keep going on until we got all the way to 6, 6, 6, 6. How many elements are in S of 4?
36.
6, 4.
6 to the 4. It's massive. So it's going to be its size, the size of S to the 4 is equal to 6 to the 4, right? Now let's look at the probability. What is the probability of 1, 3, 6, 1 equal to?
1 over 6.
By definition, the probability of some list of outcomes is equal to the product of all their individual probabilities. So that's going to be the probability of 1 times the probability of 2 or 3 times the probability of 6 times the probability of 1, which is equal to 1 6 times 1 6 times 1 6 times 1 6, or 1 over 6 to the 4. Make sense? So it's just a convenience that we don't need to come up with a completely new sample space for rolling 4 die if we already have a sample space for talking about rolling 1 die. So it's just a convenience thing. We could have just created a new sample space for rolling 4 die and called this our S and said our P just gives 1 over 6 to the 4 for each thing. So just convenience thing. All right, let's talk about binary events. In particular, we'll use the case of talking about flipping an unfair coin. So I've got an unfair coin, and I'm flipping an unfair coin. And all you know, the probability of heads now is P. It's no longer just 1/2. Maybe it's 60% chance, maybe it's 40% chance. Maybe it's a 90% chance of coming up heads. We've got an unfair coin. You with me? So the probability of it coming up heads is some number P. We don't know what that number is. Question. What is the probability of us getting heads, then tails, then heads, then tails? Maybe before we do that, really quick, what's the probability of tails?
1 minus P.
1 minus P. If heads has a probability of P, then tails has a probability of 1 minus P. So if we've got our bias clean, so heads comes up 60% of the time, then tails again come up 40% of the time.
So it's P times P times P.
Perfect.
1 minus P.
So here, what's the probability of us getting heads?
P to the 4.
Of us just getting the first heads,
Oh.
just P. Then after that we get another heads, that's just times P. Then getting a tails, that's 1 minus P. Then getting a heads, that's times P. Then getting a heads, that's times P. Which when it's all said and done, put all the P's together into 1 minus P together, that's P to the 4 times 1 minus P. You with me?
So it's P to the 4 minus P to the 5.
Sure, but we'll just leave it there.
That's negative.
P is going to be less than 1. P to the 5 is a smaller number than P to the 4.
But it's, yeah,
Did I say it's negative? I meant smaller than 1.
you did.
It's a fraction. Multiplying a fraction by itself gives you an even smaller number. A half times a half gives you a fourth. It gets smaller. Okay, now let's do this one. What's the probability of getting tails first?
Just 1 minus P.
1 minus P, perfect. Times P times P times P times P, which gives you the exact same thing, P to the 4 times 1 minus P. And so the order where it was a list of independent events like that didn't matter when you calculate the probability of a string of events. All that really depended on was how many times T and H each showed up. And we'll be doing a lot more with that concept next week.
Okay.
Okay, last problem now is the Monty Hall problem. This was a game show that they used to do. The host had a name, Monty Hall. And when you won, or something at the game show, had a chance for a prize, he had 3 doors. So we have 3 doors like this. And now behind one of the doors was a car, and behind 2 of the doors was a goat. Right?
Yeah.
So it could have been go behind this door, car behind this door, something like that. Now when the person playing on the show got a chance to choose a door. So they choose a door, let's say that they chose this door. then Monty Hall would go to a door that for sure didn't have the car behind it, and he would open the door and say, there's a goat. There's a goat behind this door. Do you want to stick with your choice, or do you want to switch to the other door? And they got to choose, should I stick with my door or should I switch and try my luck with the other door? So they don't know. They know one of them has a goat, one of them has a car. Should they switch? Should they stick with their guess? Does it matter? Is it still 50-50?
They should switch.
They should switch, it doesn't matter.
Because the odds of getting 2 goats in a row is...
Well, they don't know.
Oh no, they shouldn't switch.
They don't know. So most people wouldn't switch. They thought that he was trying to bait him. They thought that he was trying to bait them into switching. So they wouldn't switch. But the question is, should you switch or should you stick with your initial choice?
Well,
Or does it not matter?
How many of the cards on that one? Of course you switch.
Right, so forget where those are. All you know is, you chose this door. I say, okay, there's a goat over here. Should you stick with your choice or should you switch?
It doesn't matter. It's still 50-50.
It's still 50-50, right? The answer is, you should always switch.
Why?
And we're going to try and make that intuitive now.
Your intuition sucks.
Yeah, that's fair.
So, here's what we're going to do. Who wants to play the game?
I'll do it.
All right, you can play the game.
Give it back, Jared.
I need one of you to write a list of random numbers. Write a list of random numbers 1 through 3.
Phoenix will do it.
So like 1, 3, 3, 1, 2, 1, 1, whatever.
Yeah.
And you can't look at the list.
Okay.
How many?
Debbie, you're the game show host. You can see the numbers. Right?
Okay, so wait. What?
You're just writing a list of random numbers between 1 and 3.
1 and 3.
Yeah.
Okay.
So something like 3, 2, 2, 1, 3, 1. A list of random numbers between 1 and 3 that Debbie can see. You're writing what door the car is behind.
Me?
No, he is.
Oh.
So you can see what door the car is behind. And you're just going to go down the list.
How does that?
Why are there so many numbers?
Because we're going to play the game over and over again. For you to get a sense for why I'm always going to beat you. Or why my way's better. Now, me and you are going to be playing, but we're going to be playing in like parallel universes. So we're both playing the same game. The only difference between me and you is you're going to always stick with your choice. I'm always going to switch. And we're going to see how often we win.
Interesting.
All right. So
How many rights am I writing?
I'm not playing with Jeremy. I'm playing with Chandler.
Facts, you don't want to lose.
Because I don't want to lose. Pick on the little brother. All right. And we're just going to keep our score here.
Okay.
So, to begin with, pick a door. You're going to pick a door 1, 2, and 3. You don't need all that space.
Here, let's see this.
So here's door 1, here's door 2, here's door 3.
No, she says.
Okay, so you pick a door.
Door 3.
So he picks door 3. So here's his pick. He picks this. Debbie, you say which door it's not, and I also pick door 3. So you and me have now both picked door 3. We're in parallel universes. Debbie, tell me a door that's not behind.
Wait, what?
Both of them right.
One of these 2 doors for sure has a goat.
He labeled the cars, right?
No, I need to do that.
You wrote numbers 1 through 3. So you're looking at a number, maybe you're looking at the number 2, I don't know. If you're looking at the number 2, that means that there's a car behind door number 2.
Oh, that's what you mean. Okay.
So then you would say, the car is not behind door number 1,
There's a goat.
right? The car is not behind which of the, for sure, a car is not behind one of these 2.
I see it's listed.
Tell me which one.
The car is not behind door number 2.
So the car is not behind door number 2. So, you choose to stay, I choose to switch. Who won?
Done.
I won. Let's play again. She has a new number now that she's looking at.
Okay.
You choose a door.
1.
1. Tell me, so we both chose 1. One of these doesn't have it. Tell me which one.
2 does not have a car.
2 doesn't. I choose 3. Who won?
Donnie.
Because I chose 1. I wasn't that.
Choose again.
2.
2. Okay, now all you need to answer, we don't need to play it out. Either you got it or you didn't, right?
Yeah.
If you didn't get it, then it's behind one of these two doors, right? If you didn't get it, I for sure am now going to get it. You see that every time you don't get the car, I for sure get the car?
So it's 50-50 for him,
Right.
but then it's...
Hold on. So every time you don't get the car, I for sure get the car.
Oh, that's hack.
So all we have to care about is whether or not Chandler picked the car. Did Chandler pick the car?
Yes.
Yes. So in that case, you won. Which means I would have switched and I would have gotten to go. Right?
Yeah.
All right, guess again.
3.
3. Did Chandler pick the car?
Yes.
Yes.
Swipe me with the dummy.
Guess again.
1.
1. Did Chandler pick the car?
Yes.
Wow.
It's crazy how it just goes 1, 2,
He's not.
1, 2, 3.
Guess again.
2. 3.
Did Chandler get the car?
No.
There's
So
no-
I get the car, right?
Yeah, because the car's not under number 2.
Right. So every time he doesn't guess it right, I'm going to end up winning.
Yeah.
How often is he going to guess it right?
1/3.
Yeah.
1/3 of the time. So how often am I going to win?
50%.
2/3 of the time.
Oh,
If he wins 1/3, I win 2/3. And if we keep pointing this out, I'll eventually pass him up. I don't have to worry. He might get lucky in the first 10, the first 20, the first 50. Eventually, I'm going to get more than him.
Right.
Assuming you came up with a list of random numbers. It'd be better if I had a random number generator come up with it.
Still pretty random.
But, yeah, doesn't matter. Common trick. So, this is something, I think it was an MIT professor. Some professor would do. He would say, I'm going to come up with a challenge for all you guys. I want you to go home and flip a coin 100 times and write down heads, tails, whatever the coin flipped in 100 coin flips. Or just make them up. Right? So you can actually flip the coin, or you can just make it up and just write out whatever you want. Now, you can't do half and half. Either always flip the coin, or you have to make up all of them yourself. You can't do half and half. And I will always be able to tell you which ones were actually flipped versus which ones you made up. That's what he told the students he could do. How? Here's what he would look for. I can't remember what the magic number was, but he would just look through it and he'd look for somewhere in the flips where there was like, I think 8 in a row. So he would look somewhere for 8 H's in a row. Maybe it was like 6 H's in a row. Maybe that's magic number. So he starts scanning along the paper, looks somewhere for 6 H's in a row or 6 tails in a row. Because in 100 flips, it's likely that you're going to get some weird chain of sequences like that. But when human beings write random numbers, they don't want to do something like that.
Yeah.
Their brain tells them something like, that's not random. So that's all he did. He would look through the paper, see if he could find a string of 6, I can't remember his magic number, but it was like 6 or 7 or 8, some magic number like that. That was very likely to have that. He'd just look for that chain, and if it wasn't in there, he'd say, you made it up. Or he'd say, okay, you actually flipped it. You made it up. You actually flipped it. And he'd get it right most of the time. And blow his students' minds. Alright. Anyways, that's the end of this section. Next section. Next section is on random variables. Now, everyone who gets stuck on probabilities gets stuck because of random variables. It's the most important section for you to read in probabilities, the next section.
Okay.
And it's what opens the door to all the cool stuff we can start doing, because after that it's going to be expectations. So, for the love, please, I know you're not going to for some reason, but for the love, please, read at least a section on random variables. It's one of those things, yeah. It's one of those things that the first time students go over it, for some reason, they just don't get it. It confuses them, even though it's really simple. And the second time, then they're like, oh, that's obvious. It's like when I tell you guys about radians. I tell you about radians, the first time you hear about radians, you're like, oh, that's so confusing, doesn't make sense. Then I tell you about it again, and you say, why didn't you explain it that way the first time?
Yeah.
Like I did. Random variables, it's that kind of thing. It's not dense, it's not hard. I'll even tell you what they are right now. It's going to be a function x, a real random variable from, is it just from S to R? I need to double check. But it's just a function to the real numbers from your space. Just a function. Nothing complex. Always confuses kids. So please read the section. It's weird because we're going to treat these functions as variables, and that's the thing that throws them off. They want to think about it as a number when it's really a variable. So read it, read through the examples, force your brain to think about that x correctly, because you're going to use an x to represent random variables. X's and y's, they're functions. It's going to be confusing the first time, second time through, it's simple. Okay. And then the section after that is going to be on expectation, which is where we can start calculating all the cool stuff. Like, if you play Russian roulette 100 times, how much money can you expect to lose? And we can start doing calculations like that.
That's depressing.
Or if you come up with your own game, like we talked about some games here that were hacked, that were rigged, where how much money could you expect to win? If you can get hard people to play it, stuff like that. So that'll be the next two sections, and that will end probability.
Did you see that thing where the guy, he sold a $20 bill to a crowd of people, and he made like $5,000 off of it? Because it was like